Here it is. Yep. Okay, so now the session is recording. Okay. So, theory, ISO 9613. ISO 9613 calculates the downwind noise level based on the equivalent sound power level minus the attenuation. That's the basic formula. ISO calculates a downwind noise level. The attenuation is split up in several attenuations, the geometrical diversion, air absorption, ground absorption, etc. And those are all familiar with you, but most importantly, ISO calculates the downwind. Of course, it's not always downwind. Downwind means a good propagation. You can hear the source at the strongest. But if you're upwind, then the ground itself can act like a barrier. And you could end up measuring, for instance, in a shadow region. ISO cannot calculate in such a shadow region. For such calculations, you need to go to harmonize, for instance, or more theoretical calculation methods. But the empirical ISO calculation method cannot calculate in the shadow region. However, ISO has an option to calculate a long-term average, for instance, over a year. And that's being handled by subtracting a meteorological correction from the downwind noise level. And this meteorological correction is a very simple formula. It's based on a local factor, the C0, and then it's depending on the source height, the receiver height, and the distance between source and the receiver. And in several countries, like the Netherlands, for instance, they subscribe a fixed C0. For instance, in the Netherlands, C0 for industrial noise is always 5. That means that the difference between a downwind noise level and a long-term average can be up to a maximum of 5 dB. And close to the source, there is not much influence on the meteorological correction, but further away from the source, there is more influence of the meteorological correction. In Predictor, we have implemented several ways of handling the meteorological correction. The first option is no meteorological correction, and that means the downwind situation. You can consider that as a kind of a maximum noise level that can occur. During specific meteorological conditions like temperature inversion, you could end up a couple of dB higher, but mostly a downwind can be assumed to be a maximum value. A single value for C0, like 5 for instance, for industrial noise in the Netherlands, that's based to calculate the long-term average. C0 per period. You can also change the C0 per period in Predictor. Then there is a concave meteorological correction implemented in Predictor. That's also meant to calculate a long-term average, but also this concave per period can calculate the worst case scenario with such a temperature inversion. And I think you can end up to a maximum of 3 dB higher than the normal downwind situation of ISO 9613. Then there's also an implementation of the C0 based on wind statistics. That's also meant for a long-term average, because then you give a statistical occurrence of wind directions over the day, evening, and night per 30-degree steps, 30-degree angle steps. So if you look at the attenuation, like I said, several attenuation terms. Geometrical diversion is the strongest. 100-meter distance, you're already 50 dB lower. This term is already 50 dB, around 50 dB on 100 meters distance. So that goes fast. Atmospheric absorption, that's depending on the frequency. Not so much absorption in the lower frequencies, more absorption in the higher frequencies. Then you've got the ground attenuation based on the source, the middle, and the receiver region. And then you have to know the reflection factor. If it's hard ground, if it's porous ground, mixed ground. In Predictor, you can define your ground factor per ground region. Then if you look at the formulas for the ground attenuation, and that's interesting, you see that they are empirical formulas, all kind of E powers. So these are best fitting curves through all kind of measurements that had been performed when they made the ISO 9613. Many measurements over different type of ground, and then they come up with a best fitting curve. But of course, that's an empirical method. And then if you look at an example, and that's always interesting, the difference between a full reflective ground and a full porous ground for source and receiver at 2 meters height and a distance of 100 meters, you see that a full reflective ground will increase your sound pressure level with 3 dB. However, a full porous ground, you will get a reduction of 3 plus 10, let's say 13 dB compared to the reflective situation. So if you make a mistake in an ISO model, instead of reflective, you make your ground absorptive, porous, then you make a mistake of 13 dB in the 250 Hz octave band. And the 250 Hz octave band is in many times the dominant octave band over longer distances. Because longer distances you lose the high frequencies and you keep the lower frequencies. So this is good to realize and to remember that it's quite sensitive. Then barrier attenuation. The ISO says for a single barrier there are maximum screening of 20 dB, and for a double refraction it's up to 25 dB. Why is it a maximum of 20 dB? Because also when you have barriers that are infinite long and infinite high, you still have 20 dB as a maximum barrier attenuation. And that's because the ISO assumes a surface density of 10 kilogram per square meter. And with a 10 kilogram per square meter, you always have a transmission through the barrier because it's not such a very thick and high density. So you always have a certain transmission loss through the barrier. And that's why even though the diffraction can be much higher, the screening due to diffraction, because you still have the transmission loss, that's why it's a maximum of 20 dB. And 20 dB for double diffraction. And in real life, of course, barriers can have a higher or lower density. However, that's according to the ISO 9613, that's not possible. That's why we added an option in Predictor to calculate the effect of a specific transmission loss. And then you can compare different barriers with different density and different transmission loss. It's a bit theoretical, but it really works because what we've done in the calculation setting, first of all, in the barrier, we have got the option to calculate transmission loss. You check this box and then you can enter the specific transmission loss for that barrier. However, in able to make a workaround around the formulas of ISO, you have to increase your maximum screening, and that's why there's a checkbox in the calculation settings to go outside the ISO. So you uncheck this one, and then you can put the maximum screening on 99, for instance, and then you can really compare barriers, because then Predictor will calculate both the diffraction loss and the transmission loss, and then you've got a good way of handling. Also, what's interesting is that normal buildings, of course, will always have a higher density than 10 kilogram per square meter, and still buildings have a maximum screening of 25 dB in the normal ISO. And that's a bit strange. So you can go outside ISO if you want to. Then, to finish up the ISO 9613 implementation, and to make it more difficult for all of you, we've got 4 implementations of ISO 9613 in Predictor. This is a shot from the help file. We've got the normal ISO 9613. We've got the ISO 9613 1/3 octaves. We've got the ISO 9613 Road. And we've got LimA ISO. The first ISO was the original one when we started Predictor in 1996. Then we added the 1/3 octave. Then we added the Road. And then in 2001, when we joined forces with Stapelfeld, the developers of LimA, we decided to add a fourth implementation, the LimA ISO implementation, to Predictor, because at that time the LimA ISO implementation had benefits over the original Predictor implementation, let's say the Predictor implementations. We kept the 3 original Predictor implementations for compatibility reasons, but over the years these 4 methods grew to each other, especially in version 12, when all 4 of them are now quality assured. So there is not much reason to choose one or the other. And normally for starting users of Predictor, I would say use the original ISO, because the original ISO starts from 31 Hz to 8000 Hz, while the LimA ISO is only from 63 to 8000 Hz. So there are some differences. Also, the ISO has more types of sources. So it's a decision you as a user can make. But if you do not know what to choose, I would say choose the first one, the Octave implementation, this one. So that was the first part. And let me just check if everybody is still here. Yeah, everybody's still here. So you're not left or fallen asleep. The next I want to show you is a little bit, let me see, where's the other one? Here. I will not show you the complete presentation, but I want to point some highlights of this paper I've been giving on several events around the world. And it's about quality assurance implementation of noise prediction standards in software, and specifically of the ISO 9613 in software. And the idea, of course, is that if one software developer implements the ISO and the other software developer implements the ISO, that both implementations give the same answer for the same situation. That's, of course, the benefit and the goal of quality assurance. And well, the paper describes why you need it. Well, that's of course for everybody makes sense. I will just go quickly through it. However, what's interesting is to realize that several standards do not even have test cases. Like the ISO 9613, like the RMR, like the Knossos, they do not have test cases. Only the CRTN has 18 test cases, and the NPB 2008 had two test cases. So it's a very poor result if you look at such a calculation standard that are used very often. So you need quality assurance, of course. Also how to interpret all kind of formulas. Yeah, the ISO looks simple, but of course there are very unclear situations. Assume that only one significant path exists. Well, I won't go into this one, but what we have done in the ISO 17534, I will just go on. And this is the ISO 17534. This is a quality assurance standard developed by an international working group, including software developers of all the known softwares around the world, with the objective to ensure that an identical set of input data will produce the same result in different software implementations. Within a defined range of acceptable deviations. That's of course the objective of a quality assurance method. So there are several parts of this method. One is general, 2 is general, 3 is specifically for the ISO 9613, and 4 will be the technical report for the recommendations on the Knossos calculation method. And we are still waiting on that report, because when that report is final, then we can check if our implementation of Knossos in Predictor and in LimA are according to this new quality assurance guide. So what's the most important part of this quality assurance for the ISO 9613 is the rubber band method. It describes a very unambiguous way to calculate the horizontal and the vertical detours. Because in the original ISO 9613 it was not very clear how to calculate these detours, and that made, especially that part, made the different implementations in CADNAS, SoundPlan, LimA, IMI, Predictor, iNoise, they could go all the way. You know, they could differ up to 10 dB. You know, it's while they were all within their rights, you can have a large difference, and this makes it better and more clear. There are also other parts in the quality assurance method, but this I think is the dominant part. So this quality assurance method describes 19 test cases, and what we did, we tested two software packages. Both software packages had an option with and without the recommendations, and then we compared the results. And so we compared the difference between the two software packages for all the test cases without the quality assurance, and then you can see what type of difference you get: 3.9, 1.8, up to 15.6 dB difference without quality assurance. And then when you apply all the recommendations of the quality assurance, you see that all the differences go away, and you go up to 1/10 of a dB difference. And this is, of course, the situation you want to have, because then as a consultant or authority, you do not have to unofficially promote a certain product because you do not want to have these differences. And that's always an unfair advantage for a certain software package in a certain market, of course. So this is the best way. You have the quality assurance, focus on the method, and then let the software developer prove that they have implemented it according to this quality assurance method. So as an authority, I would always ask of a software developer, please present your proof of quality assurance, that you are implemented it according to the quality assurance. So let's go into Predictor now. We've handled the theory. Hopefully you're still awake. And we go into the Predictor itself. Okay, I've opened the demonstration project, and as you all know, through the welcome dialog, you can always open the demonstration project or install it. And first of all, I want to show you the source types of an ISO 9613 model. So I go into this version, Schie Harbor, and I click on New Model. And here you see all the several standards, calculation methods that are implemented in Predictor. And so here you see the three ISO implementations, the ISO octave, the 1/3 octave, and where is the other one? Here, the road implementation. And then the fourth is the LimA ISO implementation. They are a bit ordered, industrial noise, railway noise, road traffic noise, but that's not really relevant anymore, because you can also use the ISO for road traffic noise if you want to. So it's not really true. But anyway, we're going to create a model according to the ISO 9613. And per default, Predictor says initial model. Say OK. It's added to the list of models in this version, Schie Harbor. We're going to open the model. So we start with nothing. And here are all the object types and source types that you can enter. So you can, of course, also drag such a speed bar on top of your model if you like this. So what you have here is an area source. An area source, that's a source with a sound power level, either per square meter or a total sound power level. That's an area source. Then you've got an emitting facade. An emitting facade is in fact a rectangular surface that has also a sound power level per square meter. The benefit of an emitting facade is that you can do an indoor-outdoor calculation. So you can start, because it's assumed, an emitting facade is assumed. Let me just enter a building. Just entering a building over here. Make it 5 meters high, or let's say 10 meters high. And normally when you enter the emitting facade, let me just do it again, then you also put on the snap option. You want to snap it 10 centimeters in front of the building. So you go close to the building, you see the little circle. You're now within snapping distance. And this is your emitting facade. And so now it's nicely put in front of the building at 10 centimeters distance. An emitting facade like I said, has a sound power level per square meter. Can also have a total sound power level, but you can also do an indoor-outdoor calculation. And then you have to key in your indoor sound pressure level, the reduction, and the reduction you can choose from a list of materials that's available in Predictor. You can also add your own materials, for instance, glass, 8 millimeter. And then you can, and then if you have a sound power level, a sound pressure level here inside, let's say it's a very high sound pressure level. Just typing random numbers here. And then Predictor will calculate the outgoing, the emitted sound power level. Then it will calculate your noise contours, etc. So that's I will stop the thing. That's an emitting facade. Then you've got an emitting roof. That's a similar as emitting facade, but an emitting roof also has an indoor-outdoor calculation, but that's a surface put on the roof. That's most likely you will then use the relative to item directly below and put it at 10 centimeters distance, because then automatically, if you go into the 3D view, automatically your emitting roof will be put on top of the roof. And here's your emitting facade, and here's your emitting roof. An emitting roof, that's now defined as relative to item directly below, the height. The height is relative to the item directly below, and we'll see that the item below is 10 meters height. That's the building. So that's the emitting facade. Then the line source. Well, the line source is a more normal source. It's a line, of course. There's a height. You have to give the maximum distance between the individual sources. By default it says 25. And of course the sound power level, either per meter or a total sound power level. And of course the working hours, how many hours in the day, evening or night period this source is active. And coming back on the distance, you then also see how this line source is split up into point sources during the calculation. So that's why we have put all these red dots, that you as a user are aware that during the calculation, because ISO 9613 can only calculate point sources, that during the calculation this one is split up in these point sources. And if you make your distance longer, let's say 75 meters, then you will see that there are less point sources. And that could make a difference if your calculation point is nearby. The same, the area source, also here you see all the different point sources. And when you make it 25 by 25, because this is a kind of a huge building I've put in, then you see the different point sources of the area source. So you as a user will have to decide what is the resolution of your area source or your emitting surface, your emitting facade, or your line source. Those are the three items where you have to decide your resolution in X step or Y step. Okay, that's the emitting, the line source. Then we've got the moving source. A moving source, that's an interesting source, because here you can give the sound power level of one moving vehicle. You can choose from the database that's included in Predictor. Let's say it's a medium heavy vehicle according to the Knossos. So this is the sound power level according to the Knossos method of one vehicle driving with a speed of 50 kilometers per hour. And then you can give the flow. So how many vehicles come in the day period? Let's say 100. And in the evening it's 20, and in the night it's 2, I don't know what. So, and then you see also your, in fact, your time correction, because depending on the speed and the length of the line, because the moving source is also a line, you know the time that one source will be there on the line. And then if you know that there are 100 sources, it's 100 times that time divided by the day period, 8 hours, and then the 10 log, and then you get this this time correction. It's of course going very quickly because I'm used to these kind of things, but I think you can follow me. Point source. Well, point source is a normal point source with a height, with properties, you can use, because before we did not have a separate emitting facade and emitting roof source, so we could use a normal point source as an emitting facade or an emitting roof, but you don't need that anymore. So you can just leave it at a normal point source because you have these two other source types. Directivity, you can have no directivity, so that's an omnidirectional source. You can have a 2D directivity only in the horizontal plane, and you can have a 3D directivity also going up into a vertical plane. So those are options for the directivity in 10-degree angle steps. The emission, the sound power level, and then also the working hours per period. So that's a point source. Then we also have a vertical area source. And a vertical area source is a surface that stands up with a height, for instance, of 5 meters. And then again, the height. Okay, this is the starting height. Sorry, this is the starting height, and this is the total height from the starting height. So it's 5 meters, and again, the resolution of the point sources. This one could have a no directivity or a 3D directivity because it's always how do you call it, going from the area source, from the vertical area source in that direction. Sound power level, again, working hours. Okay, so if you go in the 3D view, you see that this is a vertical area source. Where is it? It's a vertical area source over here. Zip. So and it radiates to two sides, except if you do a directivity, then it's radiating only to one side. That's how you can define such a directivity. That's the vertical area. Then the last source type, that's the wind turbine, and the wind turbine has a height, of course, of the hub height. Then you can enter the cut-in speed and the cut-out speed, the terrain type, and you can choose a wind turbine from the catalog. There's a small catalog in Predictor. You can add your own wind turbines to this catalog. And let me just choose this one. I say OK, and I can, and then mode 0. So then it will automatically fill in the sound power levels per wind speed at hub height in this dialog. Your typical spectrum, you need your typical spectrum that's going to be used for all these wind speeds. Then the wind distribution. There's a catalog of specific wind distribution. There's two defaults, The Hague and Amsterdam, but you can add your own local default wind occurrence over the day, evening, and night period. So you can also choose it from the catalog. And then Predictor will calculate the equivalent sound power level over the day, evening, and night period, because that's again needed for the propagation. But what's interesting to know is that after you have calculated, there's also what we call, but I don't have any, let me just put in one receiver over here, because then I can go to this, because there's also a wind turbine, a table of wind turbine results. So after your calculation with wind turbines, you can select the specific wind turbine and your specific calculation point, and then see the calculated sound pressure levels per wind speed. And that's interesting, of course, because then you see on which wind speed the maximum sound pressure level will occur. That's interesting to know. Okay, so those are all the source types. Then we've got objects. Let me see, how much time do we have? Yeah, we're still within time. Then we have objects. Of course, these are the calculation points. What is this? That's the contour point. Oh yeah, these are the calculation points. We've got contour points, we've got grids, we've got receiver points, and we've got vertical grids. Sorry about that. A horizontal grid, that's an area with a certain spacing. 10 by 10. Oh, that's a very low. Okay, anyway, 10 by 10 meters. So here you see your grid. You can always add contour points. For instance, if there's a line source and you want to add parallel to this line source. No, what's better is that you select it and you go to here. That's the best. The batch create items, create contour points. Then it will create contour points parallel to this specific item. For instance, at 10 meters distance, it will create a row of contour points every 10 meters. On 20 meters distance from the selected item, it will create contour points every 20 meters. You can change this. So you can generate contour points. And here you see that it has generated these blue dots. And now you can make your grid, for instance, 50 by 50 meter. And this also works for road traffic noise in Predictor railway traffic noise, that close to the road or rail, you want to have more calculation points, but further away, you do not need more calculation points. So then you can combine your horizontal grid with the contour points. And that's a very nice way of keeping your calculation time low while still maintaining a high accuracy of your contours close to the road. That's a good combination. Okay, going into the object types, barrier. A barrier is a polyline and with a certain height, whatever, 4 meters height, with a reflection factor at the left side and at the right side, and left and right is defined looking from the first node to the last, and that's why there's a small arrow in. If you select the barrier, there you see a small arrow between the nodes. That's the direction in which the nodes are entered. So left is on this side and right is on that side. And that's how it works on the left reflection factor and the right reflection factor. And here you also see this option to calculate transmission loss, like I explained. So here you could enter your specific transmission loss for this specific barrier. Whatever, 30, 35, etc. 40, 45, 50, well, okay. And then if you would like to calculate transmission loss, you also need, like I explained, to deviate from the ISO 9613. You have to deselect this one, uncheck this option, and then you can go to the 99 dB as a maximum diffraction effect for the barrier, because now you actually calculate the transmission loss. So now you do not have to assume this 10 kilogram per square meter, but now you can really calculate it. And that's sometimes a very convenient way of doing it. That's the barrier. The building. The building is a normal building with a height 12 meters, a reflection factor for all facades around the building, and you also can create a floating building. I will come back on that later. Then I won't go into the other ones, foliage region, ground region, housing region. They're all industrial sites. They are all specific items according to the ISO 9613. Ground region, of course, sorry, no, not foliage, but ground region is, of course, the region where you can define your ground factor. 0 meaning reflective, 1 meaning absorptive. So this is now an absorptive area. If your whole model, your complete model is reflective, then you can put here on the ground factor a 0. That means that everything outside your ground regions is 0, is reflective. So if your whole complete model is reflective, then you don't need to enter such ground regions. But of course, if the most part of your model is reflective, then you can do it like this, and then enter your areas where it's not reflective, and then you put here in, that's a grass, for instance, 1. Then you've got the height lines and the height points, and the height lines, of course, are the for your ground model. Mostly you import them. Let's say that this one is standing on a hill, 50 meters is a very small hill, and I make one larger one, and here's it 0. Just do like that. 0. Then if you go to your 3D view, then let me go with the standard shading. Then you see that this is actually put on the hill. This building here is put on the hill, and then slowly it goes from 50 meters, goes 50 meters down to 0. That's how, because I only put in two height lines. Okay, that's basically the source types and the object types. Now I want to show you the test calculation, and therefore I open this one, for instance. I'm going to take out the background map, close, and I'm also going to deselect my grid points, and also my receiver points have a label. I'm going to double click on receiver points, and I'm going to click on default. That means no label. And also my sources have a, and also here I've got the default. So now it's over here, and I'm going to drag this one back to the lower docking part for the speed bar. I'm going to close this one. Okay, so let me see. This is receiver 1. Receiver 1. This is source lorry 2. Now I want, or maybe this is, yeah, okay. So point 1, receiver 1, and lorry 2. I would like to know the exact attenuation between these two items, between this source and this receiver. Then I go into the test calculation. So I select test calculation. I select receiver 1. You can only select one receiver, but you can select multiple sources. Oh, and now I want to, why is this not opening? Yep. So lorry 2, I only want to see the attenuations between receiver 1 and lorry 2. Say calculate. Then you can select what type of output you would like to have. Mostly I select the detailed cross section. And then you've got an overview, what we call test calculation results. It gives you an overview of your settings. And then it starts by showing you the cross section between the receiver and the lorry. And it's receiver P1. Starts at 0 distance. So you see the cross section starting from the receiver at 0 distance. Then at 148 meters, it sees a building. Then at 162 meters, again the building, and that's correct, because if you go from this source to this receiver, of course you see the building twice. That's why it sets twice, and then at 183 meters, you see the point source. You also see the heights. You also see the ground factors, if the ground factor is changing, if it's going over a certain ground region, but everything outside the ground regions was reflective. And here is no crossing of a ground region. If it would be here, then you would see also the crossing of the ground region. And then you see the attenuations. You start with the sound power level per octave. Then it calculates the ground attenuation for the receiver region, the middle region, and the source region. And normally when it's reflective, it's always minus 1.5 for the source and minus 1.5 for the receiver. That's correct. And when there's a middle region, there's also a small attenuation for the middle region. And here you see the total A ground, the total attenuation for the ground. Then you go into the screening. There is a screen with a small vertical detour. And with certain with vertical detour, with a left detour, and right there's no detour. So based on these values, Predictor calculates the vertical attenuation, the left and the right attenuation, and then comes up with the total barrier attenuation. And so here you see the complete list. Then you've got also a vegetation attenuation, site attenuation, building attenuation, air attenuation, on the low frequencies, but still up to 28 dB for the high frequencies. Then you've got the geometrical diversions, the geometrical spreading. That's per octave the same, 56.28. Well, it's 183 meters. I said if it's 100, it's 50, so 183, 56. Meteorological correction, we're calculating downwind, so there's no meteorological correction, and then you add up with a sound pressure level. Then there's a reflection calculation in facade history, and here you see the cross-section for the reflection. It goes from the receiver over the building into a reflecting facade into the point source, Lorry 2. And here you see the same formulas, the same attenuations for this reflection path. Then there's another reflection path, and another reflection path, and another reflection path, and then totally it calculates the sound pressure level, the total sound pressure level per period. So that's this test calculation output is very interesting if you want to know in detail what's happening. If it's the ground attenuation that's changing or the barrier attenuation. So this is an interesting output called the test calculation. Okay. Of course, I go into very specific details, of course, but when you have done your calculation, then of course you can show your results as contours. Oops, sorry. Show your results as contours, areas, lines. These are all options to show your results. What's also interesting to know is that here you can toggle your results per group. So the main group is always all sources. And because if you look at your model group manager, you see how the sources are grouped. There are sources grouped in a group called distribution center, furniture company, oil co, and warehouse. And also, while viewing your result, you can change your active group. So these are the results only for distribution center. These are the results only for a furniture company. These are the results only for oil co. And these are the results only for warehouse. So that's also an interesting view. Okay, and then of course you can also change your active period for the day period. So these are the contours for the day period for the warehouse, or the day period for the distribution center, or the day period for all sources together. And this is then the day, this is the evening, and this is the night contours. And then the 24-hour, in this case the LDEN, this is the 24-hour LDEN period. Okay, then I want to show you one last point. Let me just do this one. Yep, okay. I'm going to this building was 10 meters height. Let's make it 100 meters height. And also let's make it floating. Because I now want to create a gap underneath the building. So I say it's floating. And then floating means that you detach it from the ground. And then you can define the lowest part of your building. And in most cases, then you have to switch to user-defined height. Because then you can decide that there is a gap of 30 meters underneath the building. Let me just do this, and I want to get rid of these height lines because in this case it's disturbing. Let me now show you the 3D. What happened if I have chosen and put the building as a floating building? What you see here is that I've created a gap of 30 meters underneath the building. And on top of that, the building is 100 meters high. I've just used large figures to show it correctly. These red lines are just the connection lines from the point sources of the area source towards the absolute zero level. That's just to know that there are point sources on top of the roof. You also see that the area source automatically went up with the building because we have defined the area source, the emitting roof, as relative to the object directly below. And because the object directly below the building went up to 100 meters, also my area source went up. So that's another benefit of relative to object directly below. So this is how you create a gap underneath a building. And similar, you can create a gap underneath a barrier. Also here you can say it's a floating object. And then here also you have to change to a user-defined height. You say, well, the barrier starts, I'm now going to exaggerate because otherwise you won't see it. Say 10 meters. And if you go to the view, 3D view, you see that there's a gap. There's a small gap. It's difficult to see, but there's a small gap of 10 meters underneath the barrier. And then on top of it, this 100 meters distance, 100 meter height. Okay, this is my complete program for today. I think I've touched points and parts of Predictor that you might not be used to. And I think that's why this session hopefully fills in some gaps in your knowledge and you have some additional points. So we have got some time now for questions. You can put a question using the chat option if you like to. So please feel free to ask a question using the chat option. Okay, there's one question. The question is, could you give an example of when would you use a floating barrier? Well, in some cases, barriers are actually not put into the ground. They are maybe temporarily put around construction works or whatever. And in some cases, these barriers are not very well connected to the ground. And there's a small gap underneath the barrier. And then you can actually calculate that effect, that the barrier is in fact not attached to the ground. Because Predictor will then calculate the detour underneath and the detour above. And it will use the dominant detour. So, and I think that's, for instance, one example when you would like to use a floating barrier. Any other questions? Okay, when there are no more other questions, then we can close the session. Maybe a little bit. Can we get a copy of the recorded session? There's one more question. Can we get a copy of the recorded session? I will send the recording to EMS, and you will have to ask EMS to send you a copy of the recorded session. And I will also give my PowerPoint that I've been using also to EMS. So you you should ask EMS. I don't know exactly how that works, but please ask EMS for the recorded session. Okay. Well, if there are no more questions, I would like to thank you for your attention, and hopefully it will help you using Predictor for the ISO 9613 calculations. I think it's a very advanced program, and with a good and user-friendly interface. I think it's a strong product. But of course, we are the developers. We always believe in our product. Okay. Well, thank you very much, and have a good evening, day, morning, night, wherever you are. Thank you. I will close the session now.